scalar?
The U1 scale. U1 prime.
I think that's what I skipped through here. Because G prime times VF, the VEV for this scalar, is the Z prime mass. And data tells you that the G prime is very weak. Okay? That's driving a very light Z prime. So in fact, data, if it's consistent with G minus 2, the VEV scale and the phi scale, the VEV scale is high, but the phi scale is actually weak scale because it's, if you take, say, okay, anyway, I did not elaborate the details, but this phi is exotic, yes, but it's a pretty normal scale thing. It's just the extra U1. It's a very nice little extra U1. It's a U1 that I like. Extra U1s I usually hate. This one I appreciate. And in this model, this is also surprising because usually exotic scalars do not couple to the top. This one does. The mechanism that we talked about does. So this is nothing in terms of indication, one event, okay? But imagine we have 100 in the center line, and we start to populate this diagram, okay? And 5 times more data, and if we have 3, 4, 5 events, we're getting somewhere, okay? And better background should show up here, okay?
So this only couples to, I mean, this carries this U1 prime charge, right?
Yeah.
And so it couples to Z prime. So what else does it couple to?
Actually, it does get emitted by the top. So this is the paper that I want to finish from Messiah. This T to C Z prime emission,
yes.
it can emit a phi.
Yes.
Okay. Put it this way: for L minus L tau, this phi is like the Higgs 1964 paper scalar field for abelian gauge theory.
Yeah.
Okay, except the charge is different. Everything else is the same. So this is the Higgs-Higgs in the 1964 paper, not the standard model doublet. Okay. Okay, this part was for experts.
Sorry, could you just remind me what's the branching ratio of the top decaying to Z prime?
Z prime?
Yeah.
This is not how we started out, but although we have hints, even if we use hints, they are strong enough such that the Z prime, the T to Z Z prime is, that's what, this again for expert, this is for collider 40 years, 30 years from now. Right? But put it this way, suppose, there's Babar data, and suppose in the future we find a data point, okay, that maybe we even discover the Z prime, okay? Because current data, there are some very mild hints. If we have a point here, then measuring such rate decay from top is going to the source of the model. Okay. Anyway, I would say the benchmark is like 10 to the minus 7. Very rare. Okay. But SBPC claims to have, I forget how many, 10 to the, how much? 10 to the 12, 13, 14? Maybe. Okay. And also the branching ratio almost doesn't cost you. Okay. If there's no questions, you should end it.
Yeah, I just calculated something. I just tried to calculate the event yields.
Is there any coupling to the U? Is there any coupling of the Z prime to the U?
I would say you can study it, but yeah, you can turn it around and consider UT Z prime coupling and try to do that search. Okay, we didn't write that part down, but our working assumption is that we just throw away the U part. another interesting question which we did not say. Want to write another paper?
So I just calculate the event yield in the 13 TeV LHC energy scale. If we have around 200 even spend of bonding, then the expected yield is around 20 events. If,
10 to the minus 7? No.
yeah, if I use the branch ratio of the 10 to minus 7. Yeah.
Anyway, this is what John should be studying. But I don't know. He's
Just try to see the probability of research.
You're going to come back to physics now?
At least in 1 year.
Actually, this is a model-dependent result. My view of a T2C. So here we motivate a Z prime as extremely light. What I told John is that you have done the T2C Z study. So you can change the study if there's a heavy Z prime. It's like the Z study, but now the branching ratio is different. You don't know the Z prime mass. That's a heavy Z prime. This study is totally different. You have, at production, parallel mu plus mu minus, and relatively a two-body decay. So the analysis is not going to be the same as this T2CZ study. So, and then the branch ratio is much more favorable, so what you can do about it. Now, if the Z prime has the pi zero mass, then there's no way to study it. Okay.
I think we have one question.
I know Masaya now is studying dark matter. So I'm asking whether you have you considered the possibility of Z prime in the dark photon. And
Now this is, I wrote somewhere this is not dark because it decays pretty fast. Okay.
Okay.
So we did not spend much time studying it. Because of a Japanese paper, Masaya was interested in a 3 MeV Z prime. Then that one is much more long-lived. Okay. But I ruled out studying that here. I said, Occam's razor. And also because the G minus 2 is a strong motivation.
Yeah.
That 3 MeV Z prime was motivated by the so-called ice cube hydrogen neutrino gap, which is not yet well founded. Okay? So I didn't want to chase model space. But anyway, you can see that for light, this L mu minus L tau type of gauge symmetry is pretty interesting. Okay? It's not well studied, I would say. Okay.
Could we have this possibility also in the down sector?
Huh?
Could we have this possibility also in the down sector?
We had a possibility down here. What do you mean?
Like TC Z prime, we could have some B to S Z prime.
That was the data input. Right? We had B to S transitions and S to D transitions. That's where the constraint is coming from.
Oh.
So you didn't follow in the second half. Okay. That's why. That's what. This is coming from B, and this is B. This is K. Okay. Oscillator changing neutral current to K. Okay. And therefore, it squeezes down on this space. Okay.
Is there any further question? If no, let's thank Professor Hou again.